Hey folks, welcome back. So we're talking about types of collisions in this lecture. We talked about types of systems before, and we looked at a worked example of this in the last lecture video. In this lecture video, I want to talk about the different types of collisions we could have. So this is really separate from the types of systems. This is how things collide. And I urge you to think about two different systems, two different scenarios. The first is you're playing pool, you're playing some billiards, and you shoot, and the cue ball, the white billiard ball, hits another one of the billiard balls, and basically almost transfers all of its momentum off, right? It just smack, boom. Now think about a different scenario. Think about a piece of clay. Right? You're in art class and you're trying to throw clay down or whatever, what have you. Let's just make it even more ridiculous. Let's say two of you are trying to throw clay and hit clay, two pieces of clay kind of in midair. When those two pieces of clay kind of stick, they don't really bounce off each other. They deform, they stick, and then probably just drop down. Maybe a bigger piece of clay pushes the smaller one a little bit, but by and large, these are two very different scenarios, two very different situations of collisions. One in which there's deformation, one in which there's a clack and suddenly balls are flying, but nothing has been deformed. So that's kind of almost the basis. These are the two almost archetypal kind of situations here: billiard balls and putty or clay hitting other pieces of putty or clay. So the two, let's start things off with types of collisions. Let's just list two of them. We're going to talk about elastic collisions and inelastic collisions. All right, inelastic. That gets a little bit tricky to say. And inelastic. It's a lot of vowels. An inelastic collision or an elastic collision. I'll try and be very careful about how I'm pronunciating everything and enunciating everything. So with elastic, with elastic collisions, that is the archetypal kind of elastic collision is the billiard balls hitting each other. All right, there's no loss of energy in that problem. All right, and that's kind of what defines an elastic collision. There's no loss of kinetic energy specifically. There's no loss of kinetic energy specifically due to deformation. We're going to look at that in an inelastic collision, why deformation plays such a role. So what we're saying is delta Ke equals 0. So this satisfies, for an elastic collision, we not only need to satisfy the delta Ke equals 0, but of course we're also saying that delta P equals 0 as well, assuming an isolated system. Generally speaking, they will be isolated for right now. I'm always going to consider an isolated system for right now, but we already said that if it's not isolated, we just say delta P equals our impulse of the system. So that's elastic. It's kind of boring, all things considered. And I will say very few systems or collisions are actually elastic, purely elastic, perfectly elastic. A lot of times they're not perfectly elastic. They'll be approximated to elastic, and more often than not, we're actually going to see that most systems are actually inelastic. So let's talk about inelastic. Inelastic collisions do lose some energy. They do not conserve kinetic energy. Generally speaking, one or more objects in the collision lose mechanical energy. I'll say kinetic energy for now. Ooh, that was too big. Ke to deformation, or just to deform. All right. So when we think about these hunks of clay that are going to collide, they're not only going to collide, but they're also going to mush together into some sort of new clay ball, right? And so that deformation, that change of shape takes energy. It takes energy to do that. Because, I mean, you think about it, the material itself is still moving, right? It's still moving around and as it changes shape. So it's using some of that kinetic energy to deform. So our delta Ke is not equal to 0, but we are still saying that delta P is equal to 0, assuming an isolated system, blah, blah, blah. So this is, I say it's two different types of collisions, but really it's a spectrum here. You can be more inelastic or you can be more elastic. Generally speaking, since elastic is such a pure definition of no loss of kinetic energy, it's really an end post. Everything else is inelastic. But there is such a thing as a perfectly inelastic. So let's actually make a small thing, perfectly inelastic. Perfectly inelastic collision is one in which our two objects stick together. All right. So the clay, that's why we always kind of talk about the clay or putty chunks hitting each other in inelastic collisions. It's archetypal of a perfectly inelastic collision. You can have inelastic collisions that don't stick together. Something like I'm trying to think. Something like a car crash. Honestly, it's not exactly a lighthearted example, but if you have a car crash, you can have a recoil, but there is now deformation. There is damage done to your car as you recoil, as you collide, and then you recoil. So something like that is actually a really good example of how you can deform, but still bounce to a certain extent. I know we don't think about cars bouncing very much, but that's kind of what's going on here. For a perfectly inelastic collision, our two objects that collide are sticking together. That's kind of how we're thinking about this in colloquial terms. We stick together. We take two objects and we make them into effectively one object, which is nice because if we think about our system of equations here, m1v1i plus m2v2 v2i is equal then to m1 plus m2 vf. They share the exact same velocity, final velocity, and they're moving as one. That's the whole thing, right? They stick together. They have to be having the exact same velocity. Otherwise, they're not sticking together. And so that actually simplifies our equation quite a bit because it takes a variable out of the system, right? Instead of having v1f and v2f, we just have vf. So perfectly inelastic collisions are actually really kind of easy to work with. The last thing I want to say is that a perfectly inelastic collision also describes something, a collision in reverse, more commonly known as an explosion, right? I can talk about explosions using perfectly inelastic collisions because instead of sticking together at the end, I have something that sticks together at the beginning and then blows up, right, and becomes two things. So it's like an inelastic collision in reverse. And it's the exact same math. The only thing is the F's and I's basically switch there. So those are the two types of collisions that we're really going to focus in on. 2.5 types of collisions that we're going to really focus in on in this class. Next lecture, I want to kind of dive into elastic collisions just a little bit because there is a useful expression that we can use. I'm not going to derive it. It's in my notes, but I'm going to talk about the system, the very specific situation that we can use this expression in. So I will see you next time. If you have any questions about this, feel free to email me or come to an office hour, and I'll see you next time. All right, bye.